Everyone, so in this video I'm going to go over the mortgage dataset, which is an application for the binary dependent variable model. The mortgage dataset, you have the description. Once you click on the quiz, you will get the description of the dataset, which is basically done in the year 1990 on a cross-section of 2,925 applications, mortgage applications, by blacks and Hispanics, and it's a randomly selected sample. And it's very important to read, of course, everything, but I'm not going to go everything. I just want to highlight the things that you need to look at. So the variables, here we have a detailed list of the variables. The variables that you have are like named in S's. So you have like S3 is the type of the loan, S4 is the purpose of the loan. So if S4 is taking the number 3, then it's for refinancing. If it is 1, then it's for home purchase. And then you have other variables all in S's. For example, S18 is the type of the purchaser of the loan, and so on. Okay, of course, I'm not going to use all of these variables. We're going to focus on a couple of these variables for our study or our practice. So it's very important to just have a look at the variables. It's very important to have this like Word file open. So when you're reading the question and you're not sure what is, for example, school variable is measured of, so you know it's basically years. Okay, so things like that. So you need to keep this one open or somehow available, maybe printed out next to you in case you want to refer to it. So let's start. So the first question, I'm asking you to use the mortgage dataset. You have it available in a DTA and a CSV format. And we are going to test the probability that the person is denied for mortgage application. Okay, so this is our dependent variable. This is an application for a binary dependent variable, so it's either yes, accepted for the mortgage application, or no. So it's a variable that's just a dummy variable that takes yes, 1, no, 0. Okay, and then so we're going to test this dependent variable for a person who is single, so he's not married. So we have, when you read the description of the dataset in this file, you will find that we have a variable called married. When it takes 0, then we're talking about a single person. And another variable, which is the payment to income ratio. What is the percent out of your income is going to payments? Of course, if this number increases, this would decrease the probability or increase the probability of deny. If you are paying more and more out of your income to other debts, then this would decrease increase the probability that you are denied from the mortgage application. So I'm kind of giving you a story. So I'm asking you about the probability of deny for a person who is single with a payment to income ratio at the means. And it's very important to understand what is at the means. So all the variables that we have in our model, we can compute for it an average, and I'm asking you to plug in the average for this variable. Okay, for the single variable is just a 1 and 0, so I'm asking you to plug in 0. So for this variable it's going to be for 0, and for this variable we're going to use its average. And you need to compute the predicted probability. So when you go to Stata in the do file, again, so by now you already know what is clear, what is set more of, and then I did create my directory, the path where I have my files, and then I'm using and I created the log file, which is used in order to have all the commands and all the results together. And we have I have a TTA file, which is the format of the data I'm using, and I have here another option. It's in green, so it's not going to be executed in Stata, and I'm just letting you know that if you want to use a CSV format, then this is the command for it. Okay, and then we start to have our data set, and the data set, as I said, it's defined in S's. So you will start to have, okay, I'm going to generate a variable which is called deny, and deny is equal to S7 when S7 is equal to 3. So if you want to understand what does that mean, just go try to find where is S7. Okay, S7 is right here, type of the action taken. S7 type of the action taken, and I'm focusing on this as my dependent variable. So I'm creating a dependent variable that will take 1 if the application is denied. And this is like the concern of what we want to test, our concern in this study. Okay, you can of course create any other dependent variable, but this is what we're going to focus on in this practice. And we have other payment to income ratio. Okay, so you have all the definitions right here. You can go ahead and take one by one and then refer to the Word document and make sure that you understand it. These are creations of variables or dummies um, out of your data set. So to answer the first question, we need to, okay, so to answer the first question, all of these are probably like extra information for you. If you want to have linear dependent variable, of course, the first question is just asking you about the probit model. So if I'm asking you about the probit model, this is the start of, where the question is asking you. So we need to have to generate the mean for the payment to income ratio. So PIRAT is the payment to income ratio. In order to generate the mean, we basically, let me first run the first couple of commands to get the data set in. So I'm going to run these. Make sure don't run this one because I don't have any log file open. So if I click on this one, it will give me an error message. So just, I don't have any log file, just open Stata. So this one is not going to be executed. Okay, and then I have the mortgage DTA. So I'm calling the data set. Here, as you can see, all in S's, we haven't defined them yet. Next, what we want to do is to define the variables of interest. The next step is, I'm not going to click on these. You can feel free to practice this part, but I'm focusing on the probit model now. I need to create the mean of the payment to income ratio. In order to do that, you just get the summarize command for the payment to income ratio, return list of all statistics, and then generate a variable called pi rate mean, which is R mean. This would give me the average for this variable. As you can see, the R mean, this is our focus, is equal to this number. And this one is telling you that, I would say, 33.29%, which is about approximated 33.29% of all our applicants, 33.29% of all the sample that we have, they have this payment to income ratio at this number. So the average of the payment to income ratio is 33.29% of all the observations. In other words, the average person in the sample would pay out of the income 33.29% to other payments, to debts or other things. It's very important to make sure that we are using this variable, which is the payment to, the mean later on. So let's try to estimate the model. To estimate a probit model, instead of having regress, we have probit, then dependent variable, then the two independent variables that we have, and then I'm adding a robust standard error. So you get this, like this table with these results, and then the next thing that you need to do is to compute the cumulative normal distribution given the information I'm asking you to do. So as you had on the slides, in order to do that, you need to have the cumulative standard normal distribution, and inside it you have the betas multiplied times the variables that you need. So we have the first one, which is the constant multiplied times 1, or just the constant, plus the beta of the parameter, beta, which is the parameter of the payment to income ratio, multiplied times the payment to income ratio at the mean, which we have created right here, okay, plus beta married times 0. So that means when I create the scalar, which is z0, would give me the probability of the person who is single. And that's what I'm calling here. Display the probability for a single at means or single person at means, then it's the normal probability distribution or the cumulative normal probability distribution of the Z0, which is right here. And then you can, so let's try this one. So we're going to create this one and then run it, right? It's going to give us the scalar right here, but we want the normal probability distribution of this thing. So this would give us about 15.77% probability of deny if the person is single. And the answer is right here. So when you want to check the next question, which is what about if this person is married? We would expect a married person to have less probability of being rejected, right? Single usually have a higher probability of being rejected for a mortgage application. So you go to scalar, and then what you're going to change is, so of course you're going to have the same Z0 that you used to have before, but then the only change is this coefficient is going to be multiplied times 1. Of course, when it's multiplied times 0, it's not there, right, in this part. But if you want to make it appear, then multiply it times 1, right? And then we're going to run this part, and when you run this part, you will get the probability of, right, the probability of married. So the probability of married is about 12%, or in the answers here, I don't approximate, so you will get right here exactly the same number. So this is the probability of single, this is the probability of married, and the next question depends on the first two. I'm asking you what is the predicted change in the probability from single to married. Of course, you would expect a drop, right? So rejection here is higher than a rejection for a married person. So you would expect a negative, like if you don't run anything, just you would, like, it makes sense that it's going to be either B or D. Why? Because we expect a married person to have less probability of being denied for a mortgage application. You would expect this number to be smaller than this number, or the answer, which is the difference between these two, would be like from being single to married, you will have a negative sign, right? So, or the drop in the probability would be the difference in these two. So the difference would be here. The difference would be a drop from single to married by about 3.87%. So the answer is right here, D. The next question is, we're just adding another variable to the model. So we have the dependent variable, probability of deny, and then married versus single. So I'm asking you about the difference now of a person who is married versus single with a payment to income ratio, again at the mean, but I'm adding education. Okay, so we are adding now the impact of education. And you would expect, if I have education, the probability of deny, right, would even be higher when the person is, the gap between a single and married would be higher, right, when the person is having education. So you can run this one here. I have the variable high school. The variable high school is a dummy variable that takes one if the person has 12 years of education or more, right? And then you multiply it times basically the coefficient times 1. So the question is just asking you about the change. So the question is kind of asking you about this part only. But in order to get this part, you have to get the first and the second. So when you run this part of the model, right, you would get that the difference in the probability of deny from a person being single to a person being married with education, the drop is even bigger because education matters, right? So that would be answer number A. Okay. The next thing is we're going to repeat the whole same story, but with a logic model. So remember, the first question was asking about single, second question was asking about married person, third question was asking about the difference, and the fourth question was asking you about the difference again, but with education. So we're going to repeat the same thing. So person who is single. So a person who is single, so I'm just having here a model, deny, payment to income ratio, married, and then robust standard error. We're going to create a scalar which is different in name than any other scalar before. And again, constant times 1, payment to income ratio at the mean as the question is asking you, and then we're talking about a single person. And then we're going to repeat the same thing. We call it different scalar that takes W0, but then now married being multiplied times 1. And then we're going to have the probability for a single at the mean, the probability of married at the means, and then the difference in probability. Again, the question is asking you only about the difference, but in order to get to this point, you have to run each step before that. So we're going to run everything, right? And so the question is asking you about the difference. So the difference between, I'm sorry, I just got confused. So the question is asking you about the probability for single at the mean. So this is question number 5. So the answer is right here. So this is the probability of being single, okay, estimated by a logic model. The probability of being married, estimated by a logic model. This is question number 6. C. Question number 7 is asking you, like again, same story as we had with the previous probit. With the logic, we're asking about the difference between being single to a married status. Of course, you have a drop in the probability of deny. So you would expect a negative answer before you start. It's either B or C. So the difference would be about negative 3.6%, and the answer is right here, B. Again, question 8 repeats a previous question in which I'm asking you, what about education? Will the drop be bigger if we have education? You would expect the drop from being single to being married would be even bigger, right? If you have education. In other words, a person with education has less probability of being denied. So the negative, you would expect again a negative sign in this answer, so it's either B or C. So in question number 8, we're looking again about the high school variable. So it's added to the model. It's a dummy variable, and we need to run this part, which is after adding the high school education. So after you add the high school education, actually the question is only asking you about this part. As I told you, you would expect the drop to be even bigger from the previous case. The previous case was about 3.6%. Now it's 3.8%, a slightly higher number. So education matters, right? So if you have education, the probability of being rejected decreases. Okay, and from single to married both decreases, but the jump between single and married, right, gets more negative, or you would have a bigger drop. The last question, question number 9, you were asked to the F statistic to test the married dummy and the education variable are jointly statistically significant. So you want to test the joint significance of the married dummy and education. To do that, it's very simple. You perform an F test, and the F test is, again, it's based on the logit model, so you need to run first the logit model and then do the F test by the command test PARM. And you run this one, okay, and when you run it, you will get the results here. This one is telling you there is the test statistic, which is the F statistic, which question 9 is asking you about. What is the F statistic for the test? It's right here, 17.57. And question number 10 is asking you about the meaning of the results of this test. So as you can see, the probability of this statistic is very small. In other words, there is a very small probability, and when I say very small, it's smaller than 10%, it's smaller than 5%, it's smaller than 1%, so it's smaller than all conventional levels of significance. So this one, there is a very small probability that these two coefficients are equal to 0. In other words, these two coefficients matter in my regression. These two coefficients are jointly statistically significant, so I need them in my regression. So the answer is right here. The two regressors are statistically significant. So anytime you reject the null hypothesis, where the null is that these coefficients are equal to 0, so anytime you're rejecting the null, you're basically, another word of saying it is that the coefficients are statistically significant. They are different from 0. Once you're done, you can just submit this one for grading. Of course, it's not graded, but it's a very good practice for you. All right, everyone, so I'm going to stop here.